Hi there. In this video, we're gonna keep working on chapter 4. And we're gonna look at statistical significance. So let's jump right in. So we saw in an earlier example in chapter 4, the PowerPoints, where a market researcher took random samples of size 200 to test the claim that 81% of adults in Lorain County have smartphones. In that example, the alternative hypothesis was the alternative was P not equal to 0.81, and sample statistics farther from 0.81 provide stronger evidence against the null hypothesis and in support of the alternative. So that's what we saw in that example. And if you forgot that example, you can go back and check it real quick. We just took 3 different samples from the population and decided which one of those samples provided the strongest evidence against the null hypothesis. Well, what we can do is we can use StatKey to generate randomization tests for these sample statistics, and we'd actually get p-values. So one of our samples in that example from earlier in the slides was 174 out of 200. That's 0.87. So you'd go into StatKey, make the randomization distribution, click 0.87. The alternative hypothesis is not equal, so you click two-tail. So your p-value is 0.019 times 2, so you get 0.038. So this is the probability of getting this sample statistic, or one more extreme, if p equals 0.81 is the true parameter value. So remember, we're interpreting p-values as the proportion of sample statistics that have this quality of being at or more extreme, or the probability of obtaining a random sample statistic and having it be at that value or more extreme. And then one of the other samples was 0.154 out of 200, 154 out of 200, that's 0.77. Its p-value is 0.194. So here we have 2 different probabilities for 2 different sample statistics. This is a two-tailed alternative hypothesis, so we're looking on both sides. And we can see that sample statistics farther away from the center have smaller p-values. In that problem earlier, the smartphone example, there was another market researcher or another sample that its sample statistic was 0.67. 0.67 wouldn't even show up on the graph because it'd be way over here, so that would be a p-value of 0. So I didn't even do that one because it's not interesting. So I showed you the other 2, right? So there's 0.87, 0.77. So the closer to the null hypothesis that your sample statistic gets, the larger your p-value will be. So what we do now is we just cut out the middleman, and we say p-values mean that there's a smaller proportion of sample statistics in the distribution that are at or more extreme than that value. We interpret that as the probability that any particular one of those sample statistics was selected at random. That is an unlikely event if a p-value is small, and then we interpret that as strength of evidence against the null hypothesis. So we don't want to say that whole long chain of argument every time. So we cut out the middleman and we just say the p-value is directly how we interpret the strength of evidence. Smaller p-values are stronger evidence. If you need to remind yourself why, go back and study everything else in chapter 4, because we've been setting this up in the first 2 sections. From this point forward, though, we don't really use the definition of p-value too much. We just say small p-value, strong evidence, right? If the p-value is small, reject the null, right? It means the null is not true. So in example 1, p-hat was 0.87. That was strong evidence in support of the alternative hypothesis because the sample statistic is unlikely to be the result of random chance. right? So small p-value means low probability of occurrence. Low probability of occurrence means the null hypothesis probably isn't true, right? Or at least that's sort of a unofficial way of interpreting it, right? Because you're weighing the null hypothesis versus the alternative. So small p-value is, it's unlikely we got that particular sample statistic with a true null hypothesis. And what happens is we end up interpreting that sort of unofficially as the likelihood that the alternative hypothesis would be true. I mean, it's not that in a very like mathematically precise sense, but that's sort of how we interpret it. And then second bullet, if p hat is 0.77, that's weak evidence in support of the alternative hypothesis, because the sample statistic could reasonably be the result of random chance. So all we have to do now is come up with a benchmark of how small a p-value has to be in order for us to conclude that the alternative hypothesis is true. Because here, if we go back, let's just look at example 1 again. We're saying that this is not strong enough evidence because you can see about 20% of the dots are red. So there's about a 1 in 5 chance of getting that sample statistic just randomly. But 1 in 5 is not particularly unusual. Here, we're saying about 4% of the dots are red. And now some of you are remembering the 95% rule. That's sort of what we're doing here. On a two-tailed alternative hypothesis, we're doing something similar to the 95% rule. Anything outside the middle 95% is unusual, and that's actually where we're going to set our initial benchmark for the evidence being strong enough. So if it's outside the 95%, then we consider that strong enough evidence. It's not quite that simple, but that again, that's our starting benchmark. And that leads us naturally to statistical significance. If the p-value is small enough, the sample results are more extreme than we would reasonably expect to see by random chance if the null hypothesis were true. If this happens, we say the data are statistically significant. Statistically significant data provide convincing evidence in favor of the alternative hypothesis and allow us to support that claim about the population. So what we're doing here is we're just saying that there's some point at which we're willing to accept strong enough evidence. That's it. And that makes sense, right? That's based on how everybody perceives the real world, right? Maybe at the beginning of the class, you said to yourself, I'm going to get an A in stats. And maybe right now you have a B in stats. Maybe you can get that grade up to an A. Maybe you can't. But at some point, the evidence is strong enough to convince you that you definitely are going to get an A or definitely are not. So that's the way we treat every piece of data in the real world that we use is you make a guess or a claim and you test that claim against what the evidence shows you. So at the bottom, the question says, how small does a p-value have to be to achieve statistical significance? And I already alluded to it earlier. It's something similar to the 95% rule. But what we do is we give it a name. So we call it the significance level. It's just a threshold. And anything lower than that threshold is considered statistically significant. Anything above that threshold is not statistically significant. We use the Greek lowercase letter alpha, and it's a boundary below which we conclude that a p-value shows statistically significant evidence against the null hypothesis and in favor of the alternative. Here's the most common significance levels. You can set the significance level to anything you want, but you sort of run into the problem of confidence intervals where you want to be able to compare two studies to each other. They have to have the same significance level. So these are more just benchmarks, again, or sort of agreed upon values among different researchers so that results can be compared between different studies. You can see that this alpha here, it turns out this is going to correspond to our 95% rule. This would correspond to something like a 99% rule and something like a 90% rule. You'll see how that works here in a sec. If a significance level is not specified, we use 5% or 0.05. just like our 95% rule. Let's see how to use a significance level. So what we do is when you have a significance level and a p-value, we make a statistical decision using these two decision rules. These are based on the p-value from the sample and a predetermined value of alpha. Alpha is set before the data are collected. If your p-value is less than alpha, you reject the null hypothesis in favor of the alternative. This means the results are statistically significant, and we have convincing evidence to support the alternative hypothesis. If your p-value is greater than or equal to alpha, we do not reject the null hypothesis. This means the results are not statistically significant, and we do not have convincing evidence to support the alternative hypothesis. This is one of the most misunderstood things in all of statistics. There's some mnemonics that can help you. The easy one that I mentioned earlier is if the p-value is small, reject the null, right? So p-value less than alpha, that means it's small, so smaller than alpha. If p-value small, reject the null. So that's one easy way to remember it. Another easy way to remember it is that understand that the claim we're making is always, we're always testing the null hypothesis, right? So we either reject the null or do not reject. But our conclusions are always in terms of the alternative hypothesis. So if we reject the null hypothesis, that means that we have enough evidence to support our claim of the alternative hypothesis. If your p-value is large, or too large, larger than alpha, we do not reject the null, and again, we are making a claim about the alternative hypothesis. So we always test the null, but any conclusions we draw are always about the alternative hypothesis. So that's something to think about, right? So a significant result means that we're concluding the alternative hypothesis is true. Not statistically significant means we do not have enough evidence to support the alternative. So that takes a while to get the hang of the language, okay? And more about that later in this slideshow. So in the smartphone example, we were not told what alpha was, so we just set it at 5%. The sample statistic, p hat equals 0.87, has a p-value of 0.038. Because 0.038 is less than alpha, so our p-value is less than alpha, we reject the null hypothesis in favor of the alternative. This is a statistically significant result, and the sample provides sufficient evidence to support the claim that the population proportion is indeed not 81%. Now, if your sample statistic is 0.77, we saw earlier in our randomization distributions that our p-value was 0.194. So 0.194 is bigger than our alpha value, bigger than 0.05. So we do not reject the null hypothesis. Notice here, though, our claim, we're not claiming the null hypothesis is true. We're just failing to claim that it's false. And so what that means is that it is not statistically significant, so we do not have sufficient evidence to support the claim that the proportion is not 0.81 or 81%. So this is very formal, very technical, but once you see how it works, you're always going to be choice A or choice B, always, depending on p-value relative to alpha. What makes this tough for students is that by the time we reach this stage of the class, many students are still struggling with the Chapter 3 material because we didn't go through it particularly fast, but depending on your approach to studying, it can still be overwhelming at this point. And then once we hit Chapter 4, now not only do we have 5 different parameters, 3 different alternative hypotheses, but now each of those 15 options can have 2 different choices. That means for any given study, you're going to have up to 30 different results, and each one is unique to that particular kind of study. So when you're classifying these, when you're doing homework, You have to really break everything down, go through the steps to make sure you're staying organized. And then you can't just look at a previous problem and compare it. It doesn't work that way. Because if one little thing is different, the whole problem is different. So keep that in mind, that it's hard to get enough practice doing this. So if you're feeling you're not getting enough practice, you can do the book problems that I have at the end of this section. They really help a lot. All the odd answers are in the book. So determine whether the following p-values are statistically significant at the given values for alpha. So what we're going to do here is we're going to take each p-value and compare it to all three of these alpha values. That's not how studies are done in the real world, but this is just a drill. In the real world, a study would have one alpha value and maybe several p-values. All right, but it's a lot easier to write it this way, just to go over it. Because I'm basically doing 9 problems at once here. So let's look at a p-value of 0.018, right? So is this p-value statistically significant at the 0.01 level? So if you're not sure what to do, write both numbers down and figure out which number is bigger. If this number is bigger, then it's statistically significant. If this number is bigger, then it's not statistically significant. So 0.018 is bigger than 0.01, so this is not statistically significant at the 0.01 level, but it's smaller than this, so it is statistically significant at this level. And this, of course, if it's smaller than this, it's smaller than that. So this is statistically significant at this level, right? So what you would do is you would write down the p-value and which alpha values it is statistically significant at, right? And so these are all just different thresholds, right? So this would be a weak amount of evidence is needed to claim the alternative hypothesis is true. This would be a very strong amount of evidence needed, and so on and so forth. Well, this is like a moderate amount of evidence. What about 0.180? Is this p-value significant at any or all of these alpha values? So go ahead, take a second, pause the video, decide. Is 0.180 statistically significant at any of those alpha values? Well, 0.180 is larger than all of these, so it's not significant at any of the levels because the p-value is too big. In other words, that p-value would not provide strong enough evidence to reject a null hypothesis at any of the alpha values given. Last one, p-value of 0.002. Is that significant at any of the alpha levels? Well, you can see that this number is smaller than all of these, so that means 0.002 is significant at all of the levels. And that's the way these go on the homework. Some of your homework just mixes and matches p-value alpha, alpha p-value. I just did 9 problems at once here. So all you're doing is comparing alpha to the p-value, write the appropriate sign. So p greater than, less than, whatever. If it happens to be equal, then it's not significant, but that I don't think you'll ever see that actually happen. All right, let's keep moving. So here are the steps for a hypothesis test. I'm going to show you a fully worked through problem here at the end of the slides. Your homework really doesn't do a good job of this because a lot of your homework is multiple choice, whereas a lot of this is short answer and that sort of thing. Practice the problems in the book or the examples in the section in the book. You're going to have to get the hang of how to write this stuff out in words, because on a test you're going to have to do it. So here are the steps. State the null and alternative hypotheses, including identifying variables and defining parameters when necessary. So at the very least, you're going to state the null and alternative hypotheses. Maybe you have to define the variables. Maybe you have to define the parameters. That's up to you. You do whatever you can to get the result you need for the problem. Number 2, determine the value of the observed sample statistic. So use the data, collect the sample statistic, or compute the sample statistic. Step 3, use the value of the sample statistic and the randomization distribution to find the p-value. Step 4, make a statistical decision about the null. Reject or do not reject the null. And 5, write a sentence explaining the conclusion of the test in context, indicating whether or not we have convincing evidence for the alternative hypothesis. For step 5, sometimes you want to write 2 sentences because these things can like chain out pretty big because some of these parameters are pretty big and we have lots of variables and stuff. So that maybe that should say write at least 1 sentence. All right, so let's see how to use this. So what I did here in example 3 is we're just looking at steps 4 and 5. Earlier in chapter 4, we saw how to do this. We saw how to do this. We saw how to do this. This step 4 is new in this section, and step 5 is new in this section. So this problem here, example 3, will help us with steps 4 and 5 before we get to a fully worked out problem. An observational study is conducted to investigate a possible relationship between exposure to organophosphate pesticides as measured in urinary metabolites and diagnosis of ADHD. In reporting the results of this study, the authors make the following statements. The threshold for statistical significance was set at p less than 0.05. The odds of meeting the criteria for ADHD increased with DAP metabolites, and the association was statistically significant. So let's answer these questions based only on the results of the study. We don't get to see the data. In fact, they could be using techniques we don't even learn about, but we still should be able to interpret the results. So what can we conclude about the p-value obtained from the data? Well, so we're told something about a p-value here. In a lot of professional papers, they just write capital P. Remember, p-value stands for probability. We used capital P to denote probability in section P1, right? So a capital P is used for p-value sometimes. All right, well, so the p-value is statistically significant if p is less than 0.05. We're also told the association was statistically significant. That tells us our p-value for this study must have been less than 0.05. So see how we're using the results to work backwards and kind of look at what the study must have shown. Can we conclude that exposure to pesticides is related to the likelihood of ADHD diagnosis? All right, well, we're seeing the association is statistically significant. So that tells us there's some sort of association. So, and it's statistically significant. And we're told that there's an increase. So when the criteria for ADHD increase, the DAP metabolites increase. So these are both quantitative. So that means that it's a correlation, and it's a positive correlation. Well, that's exactly what we're told. Statistically significant means more likely to be the result of an association compared to random chance, right? So this is telling us that this is not what we would expect to see if there's no association, because it's statistically significant. So yes, we can conclude exposure to pesticides is related to the likelihood. The two increase together. Again, statistically significant, and we see that there's a positive association. C, can we conclude that exposure to pesticides causes more cases of ADHD? So, does the study have the capability of showing us that pesticides cause this ADHD to take place? So what do you think? Pause. If you're not sure, pause it and think about it. We're going to the answers. So lots of these follow-up questions about causation versus association. An observational study can show association, but not causation. All right, last example, we're going to look at, let me shrink this down a little bit. These slides are big. Is owning a cat as a child related to mental illness later in life? So there's a disease called toxoplasmosis. Is a disease transmitted primarily through contact with cat feces and has recently been linked with schizophrenia and other mental illnesses. A study randomly selected 262 people registered with the National Alliance for the Mentally Ill, so it's pronounced NAMI, almost all of whom had schizophrenia. And for each person selected, chose 2 people from families without mental illness who were the same age, sex, socioeconomic status as the person selected from NAMI. So what they're trying to do here is they're trying to balance the study on confounding variables. So if they match up the ages, then age isn't a confounding variable. They match up the sexes, then that isn't. They match up socioeconomic status. So what they're doing is trying to simulate an experiment with an observational study. Each participant was asked whether or not they owned a cat as a child. The results showed that 136 of the 262 people in the mentally ill group had owned a cat, while 220 of the 522 people in the not mentally ill group had owned a cat. So here's what the data looks like. Does the sample provide evidence that the relative frequency of mental illness is higher for cat owners? So you can see here that this is a side-by-side bar chart, and you can see that we're looking at the relative frequency. So we're looking at mental illness relative to the total, right? So we're looking at how big is the blue bar compared to both of the cluster bars added together. So it certainly looks like that mental illness is higher in the cat ownership group. It certainly looks like that. But that is not proof. That is simply just one of the many things we take into consideration when we look at these studies. Let's see what exactly we have to do. So we're going to do a randomization test. So here are the samples. So I went ahead and did the randomization test. But I'm going to show you again, as I've done in previous slideshows, how to do randomization tests by hand. I don't want you to have to do the stat key. If you would like to do the stat key on your own for this problem, the data is all given. You can go into stat key and do it. This data set is built into stat key. So I did 500 randomization samples. Here's what we're going to talk about. The null and alternative hypotheses, the sample statistic, the p-value, reject or do not reject a null, and explaining the conclusion of the test in context. So the first 5 steps here, A through E, come from what we saw earlier, a few slides ago, the 5 steps for a hypothesis test. The last 2 questions are follow-up questions, right? So what you do is you do the 5 steps, you get an answer, and then you have to interpret that answer back in the context of the reason the study was done in the first place, right? Researchers don't do studies just so they can, farm for p-values. They're trying to learn about medical and psychological effects in the world. All right, let's go through it. All right, null and alternative hypotheses. So we saw earlier, if you go back, we can see that we have 2 groups. So we have a categorical explanatory variable. We can see the response variable is categorical as well because it's mentally ill or not, owned a cat or not. That's 2 categorical variables. So our sample statistic is p hat 1 minus p hat 2. Our parameter is p1 minus p2, which means our null hypothesis will be PC. So I put C for cat and N for no cat. And the alternative hypothesis, we're putting a greater than symbol here because we think that the data will show that cat ownership is linked to higher mental illness. So we put a greater than there because we think the data might show that the proportion of cat owners with mental illness is higher than non-cat owners. All right, the sample statistic, well, that's easy, right? We saw the data earlier, right? It's 136 out of 262 cat owners who had mental illness. 220 out of 522 non-cat owners had mental illness, right? So you get 0.098. Use the randomization distribution to find the p-value. All right, so the randomization distribution is on the previous slide. There's our randomization distribution. The alternative hypothesis is a greater than, so we're only going to be looking to the right. Now, in StatKey, you would click on the number at the bottom and it would count for you, but we have to practice doing this by hand so that we can do exams, right? So on an exam, this is exactly what it's going to look like. You're going to have to figure out what the p-value is. So how do we do it? Well, you go back and you say, there's my sample statistic. You need to do something with the sample statistic because StatKey doesn't know what the sample statistic is. StatKey generates this based on just the null hypothesis alone. Well, 0.098 is way over here somewhere. It's really close to 0.10. So it looks like we have 1, 2, 3 dots over here at 0.098 or higher. And remember, the original sample statistic will always show up in this graph if you have a small sample. So there's 0.098. There's 2 more to the right, 3 dots. So 3 divided by 500 is 0.006. From here, it's pretty straightforward, right? Compare your p-value to alpha. Your p-value is less than alpha, so we reject the null hypothesis. Then you just use your decision rule. Rejecting the null hypothesis means the results are statistically significant. That means we have convincing evidence that the alternative hypothesis, oh, sorry, wrong way. Sorry about that. Let me say that again. So p-value less than alpha means statistically significant, which tells us we have convincing evidence that the alternative hypothesis is true. So you have to go back and unpack what this means. The proportion of cat owners with mental illness, that was our variable, right? Our category of our variable was who has mental illness and who doesn't, is higher than the proportion of non-cat owners with mental illness. And that's exactly what I wrote here. We have convincing evidence the proportion of people with mental illness is higher among cat owners compared to non-cat owners. But there's only 2 kinds of people in this study. Now, follow-up questions. So we have convincing evidence that there's a positive, that the proportion of cat owners with mental illness is higher than the proportion of non-cat owners with mental illness. Does this provide evidence that there's an association? So we know the proportion is higher, but does that mean that there is an association? Yes. We use a difference in proportions to measure association among 2 categorical variables. So that's yes. A significant difference in proportion means association exists. Part G. Does this study provide evidence that owning a cat as a child causes mental illness later in life? The answer, of course, to this is no, because even though this study was built to simulate an experiment, it is still not an experiment. There could be confounding variables. So that's what it says. So that's sort of the full, front to back example. Stuff you might see on a test is going to be stuff cherry picked out of here. Or it could be something just like this, a 7-step problem could happen. Everything in here you computed by hand. We did not use StatKey to do any of this. I used StatKey to generate the randomization distribution, but everything else you can do by hand or by just, knowing terms and definitions. All right, almost done. So here's a mistake that a lot of students make. We just have to be careful. When a study has a large p-value, our decision is do not reject the null hypothesis. However, we never accept the null hypothesis. Finding a lack of convincing evidence is not the same as finding strong evidence in support of the null hypothesis. Hypothesis tests are not capable of finding evidence to support the null hypothesis. So this is something that is hard for people to understand, right? Because it seems like we're testing the null hypothesis and testing the alternative hypothesis. But we're not. We're only ever testing the null. We only reject it or do not reject it. That's it. You'll see why in the next example. So suppose we have a mystery animal named X, and we are given that there are two hypotheses. X is an elephant or it is not an elephant. Right? So the null hypothesis is that it is an elephant. So there's some animal behind a curtain or something, and we're going to presume that that animal is an elephant unless we have sufficient evidence to conclude that X is not an elephant. What conclusion would you draw from each of the following pieces of evidence? So we're assuming that this thing is an elephant that we can't see or hear, and you're told that it has 4 legs. Well, think about that evidence, right? That evidence doesn't support the null hypothesis because it could just as easily support that X is not an elephant. There's lots of animals that have 4 legs. But what do we say? Well, we say knowing that X has 4 legs is insufficient evidence to reject the null hypothesis. In other words, we're taking in all kinds of evidence, and we're only looking for things that will tell us that X is not an elephant. And if we don't see anything that tells us X is not an elephant, then we're just going to keep assuming it is. So A doesn't give us any information. It doesn't fail to reject the null hypothesis. B, X walks on 2 legs. So if you're told that X walks on 2 legs, what does that tell you about whether it's an elephant or not? I mean, it could be an elephant. Elephants can walk on 2 legs. But generally speaking, if you were looking for ways to describe elephants, walking on 2 legs is probably not one of the ways that you would describe it. So I would say that that is sufficient evidence to conclude that X is probably not an elephant, right? So I already said all this stuff, so I'll put all this stuff up. So that's how we do it, right? And I know that this context might seem silly because you're thinking, well, we're talking about toxoplasmosis, not elephants walking on 2 legs. It's really the same thing by analogy. You're only looking for evidence from the sample that would give you a significant reason to believe that the null hypothesis is not true. Everything else, you just don't do anything with it. All right. Then there is something called less formal statistical decisions. We don't spend a lot of time on this, but it is interesting to keep in mind. I've been alluding to this since Chapter 4 started. So for a 5% test, so alpha 5%, the formal decision is either reject the null or do not reject the null. And you can see that you get a chart like this. So these are your p-values in here, right? So if your p-values are above 5%, you do not reject. If your p-values are less than 5%, you do reject. So it's a black and white decision. But in some situations, we might feel more comfortable with a less rigid statistical decision. That will become clear in the next section why that is true. For this reason, we sometimes interpret a p-value less formally by merely indicating the strength of evidence it shows against the null hypothesis. So the strength of evidence chart, instead of a black and white boundary, you blur the boundary where like a darker band A darker color would mean stronger evidence against the null. So in example 4, we had a p-value of 0.026. This was sufficient evidence in favor of the alternative hypothesis. However, it may sometimes be more informative to state that the data provide strong evidence for this conclusion instead of sufficient evidence. This allows us to compare different treatments to each other, with smaller p-values providing stronger evidence. Right? So you can look at the chart. If your p-value is, 0.07, it's here, you'd say, oh, there's some evidence, or strong evidence, or moderate. And it allows us to compare different studies to each other and say one has stronger evidence, as opposed to lumping all of the studies with p-value less than alpha together. All right, well, that's it for this section. Lots of topics here to remember. And of course, if you need extra practice, try these problems out. They're very useful, very helpful. You're going to need extra practice writing these conclusions out in words. There's some practice worksheets posted on Canvas. I'm sure you guys have seen those. Those are completely optional. Those also give you a little bit more practice, but every little bit of practice you can get is helpful. So that's it for this video. I'll see you next time, and let me know if you have any questions. Bye-bye now.